Okay, so today we're going to do the second part of 6.5. Well, just to review really quickly what we did in 6.5 yesterday, I have it over here on the side board. We reviewed complex numbers in standard form, a plus bi, but we also talked about how we could write them in a trig form using r and theta. So we found out that that would be that form r cos theta or r cosine theta plus I times r sine theta. And then if you did your homework, you practiced some of these other things that I have up here on the board. I think the last two questions in part C, they asked you to do the work with the complex number and in standard form. So like if we had a plus bi times c plus di, how would you have multiplied that out in Algebra 2 in first semester? FOIL. When you FOIL, I squared is equal to -1, so you make that substitution, and you might have like terms that you get combined, and then your answer gets put back into a plus bi form. Does anybody remember, because this was I think number 61, which was not a nice number for your rectangular form, but does anybody remember how to divide complex numbers? Chloe?
Isn't it divide the r and then subtract the...
Well, over here it would be in trig form, but what about in standard form? Like, let's say I had some a plus bi divided by c plus di. Pierce?
That's an interesting one.
Well, how do you divide that?
You divide by d.
No, because they're not factors, they're terms.
Oh.
Heidi? The conjugate, yep. So the rule is you're not allowed to leave I in the denominator, because think about I, it's like the square root of -1, and you're not allowed to have radicals in the denominator. So you would use the conjugate c minus di, so that in the end your i's will cancel, and you'll get just a number. And then you have to multiply the top by that too. But think about all the work that you're doing in the old way we used to divide complex numbers. You got to FOIL out the numerator, you essentially have to FOIL out the denominator, and then you still have to combine like terms, change I squareds to -1s, all of that work. But the one, like I think Clay, you were giving me, the one in trig form, actually multiplying and dividing was really easy, right? Multiply the modulus, add the arguments, divide the modulus, subtract the arguments. So you might say, I actually like working with complex numbers in trig form as compared to what I've been taught previously about standard form. This is actually faster. So what we're going to look at today are these other two things I have here at the bottom of the board. I know that's hard for everybody to see. But what if you take a rectangular form, a plus bi, and you raise it to the nth power? I mean, the old version, we have two ways we could do that. Let's say it was a plus bi to the 5th. A plus bi times a plus bi times a plus bi 5 times, right? FOIL all that out, that'd be 4 FOILs. I'm not doing that, that's too much work. We did give you something else you could use. It was called the binomial expansion theorem. So you could do like a combination of 5 choose 0 times the first term raised to the 5th times the second term raised to 0 plus a combination 5 choose 1, and then the exponents go down and up. Do you remember that thing? Okay. But that's still a lot of, Pascal's triangle. That's still a lot of terms. Okay. So I'm going to teach you how to do powers and also roots, like nth roots of a plus bi, with trig form, and we're going to find out it's way easier in trig form. So we're going to start with a complex number, z equals r times the quantity cosine theta plus I times sine theta. And I, of course, I'm going to abbreviate this. We could say this is also r cos theta, just for shorthand, because I don't have a lot of space right there. Okay, if I asked you to do z squared, fundamentally, z squared is asking you to take z times z. So if z is r cos theta, we want to take r cos theta times r cos theta. And then if we use the multiplication rule that you practiced in your homework yesterday, when you multiply two complex numbers in their trig form, you multiply the modulus and you add the arguments. Well, if we're taking the same number times itself, the modulus is the same thing. So r times r is r squared. And when I do theta plus theta, I get 2 theta. So that's my multiplication rule from yesterday. Okay, let's do z cubed. Now, one way to do z cubed would be to do z times z. But we've already done z squared. So I'm going to pull my z squared answer. R squared kiss 2 theta. And if I want to have z cubed, I just need to multiply by another z, right? So that would be my r kiss theta above. Well, again, apply my multiplication rule. Multiply the modulus, add the arguments. R squared times r cubed. 2 theta plus theta, 3 theta. Oh my, I think I'm seeing a pattern. Could you predict what you think z to the 4th will be? What do you think? Say it out loud. R to the 4th, kiss for theta. Yeah, okay, now I'm going to show the work for that one. Okay, so I'm going to take the 3rd z cubed. So that would be r cubed kiss 3 theta. I'm going to multiply it by another r kiss theta, just to confirm that this pattern actually holds, because we only really have 2 things up there. But r cubed times r is r to the 4th, and 3 theta plus theta is kiss 4 theta. So now I'm pretty well convinced. Can you write on your papers a rule for z to the n? You said z to the n is equal to r to the n? Awesome. Close my parenthesis over there. Yeah. Okay, now we have written that rule based on a pattern. Inductive reasoning, we're noticing is going up by 1 in the exponent and what we're multiplying by. In order for us to actually have it like as a proof, we would need to prove for all cases, which we really haven't done a proof of that yet. So unfortunately, we don't get to name that after you. We're going to call it de Moivre's theorem, the guy that proved it. Okay. So I would label next to that somewhere in your notes that that's actually called de Moivre's theorem. This will be helpful on your homework. This could be helpful on the test. If it says use de Moivre's theorem, it's saying use the r to the n, kiss, and theta. You might like to call it Trenton's theorem because you came up with the pattern, but you haven't actually proved it for all cases yet.
How do you prove it for all cases? Like,
You know, like when I do a proof and I leave everything with n's and such. It would just be a little bit more algebra looking stuff. Okay, and remember that in the end, your theta has to be between 0 and 360. You could, like an easy one to imagine would be like, let's say in my original complex number that theta was 100. Well, if I raise it to the 4th power, then inside this kiss, I'll have 4 times 100, which is 400. And that won't fit inside that range. So if your angle turns out to be 400, what should you do? Subtract 360. Find a coterminal angle. And an angle that's exactly the same but has a different measure. So that would really turn into like kiss 40. So always kind of adjust so that your angle is within the acceptable range. Now, all this other stuff that comes with de Moivre's theorem is just like every mathematician, when we write this out, we're going to give like certain parameters for when this works. Mainly the one thing that you have to be aware of is we're only raising it to positive integers. So we're not doing fraction powers and we're not doing any negative powers. So we're saying to raise it to a positive power. Okay, let's do some example. Let's start with negative 1 plus I to the 6. Okay, now here's what you want to be thinking about when you're in this section 6.5. What form is your complex number currently written in? Standard form. So think about what I have over there on the side board. This represents an A plus BI, where A is negative 1, that's my real part. BI is 1I, so B is 1. That's my imaginary part. And in order to use de Moivre's theorem, all the numbers in de Moivre's theorem, R to the n, KISS, and theta, those are all things that we know from trig form. So probably first thing you want to do is change this to a trig form, or at least find R and theta. So you and your group members chat about how you can find R and theta for trig form.
Yeah, for theta, there's some rules that have tangent of -1. You know what I mean? 2. So like which one do you pick?
Put it in that trig form, what we did yesterday.
Is it negative? She just put negative 1 under.
Look back in your notes.
Negative
What
one
you need
squared
to.
plus
What's
one
R
squared.
equal to? What's
Yeah,
theta
that's
equal
R,
to?
but like for theta, I don't know like which angle you use. It's like you could use 3 pi over 4. No, you can't. 5 pi over 4. Is that negative though? Oh yeah, it's yes. So what do we use? That's what I'm. So you could do
Wait, so it mean
in degrees, you could use 1.5. Yeah, how do you know which angle to use? Or is it the same?
I know how to do it. So you guys did tangent inverse of 1 or negative 1, right? So on the same page you get negative 45.
Yeah.
So if it's like negative 1, 1 would be in the second quadrant. So you add 180. If it's in the fourth quadrant, you add 360.
Remember, don't try to reinvent the wheel here. All the things that we talked about yesterday are actually related really to our vector work from the two sections before. So when you want to find the modulus, that's really like the magnitude of your vector, that's R. When you want to find your argument, your theta, that's really like your direction angle from vectors. And if you relate that back to trigonometry, that's just Pythagorean theorem and tangent. Remember, A and B, in terms of R and theta, they're that component form in terms of magnitude and direction. So they're R cosine theta, R sine theta, if you ever need to switch back. Let's see, for the modulus, we're going to get square root 2. And your calculator here is going to tell you negative 45 degrees for your argument, but that's not okay to leave as negative 45 because your argument should be between 0 and 360. So remember that you have to go back to like the visual of where this complex number is, just negative 1 plus I. If I were going to plot negative 1 plus I on the complex plane, remember the real part goes horizontal and the imaginary part goes vertical. So I would go left 1, up 1. And since my point would be plotted in quadrant 2, I should do what? Negative 45. Add 180. Thank you, Olivia. Okay, so add 180. So that angle is really 135 degrees. And you can think about that like that direction angle back in vectors. Yeah, that angle looks like it's 135 degrees. Okay, so you could just go straight to de Moivre's theorem. I'm going to go ahead and rewrite this problem. So instead of a rectangular or standard form raised to 6, I'm going to say this is the square root of 2 KISS 135 raised to the 6th. Right? I've just rewritten it in trig form. And now I can use de Moivre's theorem, the pattern you just saw. R to the n, KISS, and theta, where n is 6. So it's going to be square root 2 to the 6th, KISS, 6 times 135, Square root 2 to the 6th. Square root of 64, which is 8, sure. And then KISS, what's 6 times 135? 810, which is too big to be my final answer. I've got to get it back down to an angle between 0 and 360. So to do that, I'm going to subtract 360 2 times. So it's really like subtracting 720. That's me getting a coterminal angle. So 8 KISS, what is that, 90?
Yeah.
That is Z to the 6th. Now, that's in trig form, right? And unless your directions say otherwise, I would just stop at trig form. I would be happy there. If it asked for rectangular form, you just sort of have to expand the KISS form and do the work, right? So it'd be like 8 times the cosine of 90. 0. And then 8 times I times the sine of 90. That's really just 8 times 1i. So 8i would be in rectangular form. Okay. Now you try this one. And if you get it in trig form, try to write your answer in standard form. So practice doing the conversion. So try the one on the right. If you get it in trig form, try changing it to standard form.
This is 240. Or KISS.
I got 34.
So anything you
Anyone
do
KISS
this,
240?
yes, I
Good.
then you have to go back to the, like, written faster. This is just as being as KISS 60. So that's what that GIS.
Negative 40.5.
It's just us being like, we're too lazy to write that out.
Negative 40.5. So you add 180 to that, right?
Not an angle.
Wait. I'm doing this wrong. I know. So we just put it in like this.
Yeah, well, good news in the second example, it's already in trig form, right? That's basically 3 KISS 60. And it's being raised to the 4th. So if I apply my rule, de Moivre's theorem, I'm going to do 3 to the 4th KISS 4 times 60, which as I'm walking around, I see lots of 81 KISS 240. And this would be your answer in trig form. I don't have to adjust that angle because it's already between 0 and 360. And if you want to change this into standard form, you know, I just think about it like this. It's 81 times, and then I'm going to re-expand this KISS form maybe. So cosine 240 plus I times sine 240. And then, oh, 240, that's one of the angles on my unit circle. Its ordered pair is negative 1/2, negative square root 3. So I can do 81 times negative 1/2 plus I times negative square root 3 over 2. Now you could leave your answer as a fraction, like negative 81 over 2, or it's a terminating decimal, so I might write it as a decimal, negative 40.5 minus 40.5 I square root 3. If you put your I at the back of your standard form, that's fine. I just always write it so that I never get confused that it's underneath the radical. It should not be underneath the radical. And this is standard form.
left it,
As -81/2?
yeah, and
Totally fine.
81 radical.
As long as it's negative there in the middle, you should be okay.
Can you put the I in front of the 40.5?
Sure.
Oh, okay.
Multiplication of those three things, 40.5, I, and square root 3, it's all commutative, so it doesn't really matter what order you multiply them. Okay, any questions on that? It's not so bad, is it? Now, you are responsible for Demoivre's theorem on Friday's test. So you will need to know that one. But if you think about how we derived it, just looking at the pattern, I think that helps me remember, oh yeah, it's just r to the n cos n theta. This next formula you will be provided on the test on Friday. So it's just a matter of can you use it.
Oh.
Oh.
It looks worse than it is. I'll give you time to write it down before I say anything. I wish I had a camera, like the camera they have on roller coasters.
Mhm.
For when I change a slide to something that looks scary. And then I could hand you your photo at the end of the period.
That's funny.
Wouldn't that be great?
You get some good reactions.
Wow.
Don't say whoa.
It might look like some people were actually on a roller coaster. Aside from their hair not
Which angles? What? I thought 240 was a 60. I thought you did 240 minus 180.
You did.
Oh yeah, you did cosine sine of stuff. So you just mess that up. It's game over.
That's true.
It's game.
Okay, so there's a little bit more going on this formula. So we kind of want to talk about some of the pieces that are going to be important. On Friday's test, this will show up exactly like you see it here. And I'm going to talk about one way to amend this formula that people may like. But you'll need to be able to plug into it on your own. I won't be able to tell you what anything in that formula means. So make sure that you're doing your practice tonight so that you feel confident with that. Okay, this is for, again, a positive integer n. So think about all the roots you've ever done in your life in math class. It's like a square root, a cube root, a fourth root, a fifth root. We don't do fraction roots, and we don't do negative roots. Okay. We're working with a complex number in trig form, arc cos theta. So if it's not in trig form, find it in trig form, right? Do the r equals square root a squared plus b squared, and do the inverse tangent b over a like we did on that first example. Okay, this statement is actually important so that you know how many answers to give me. A complex number that you take the nth root of will have n distinct roots. And the word distinct there means different. So if you're doing a cube root of a complex number, you will have 3 distinct roots. If you're doing a fifth root, then you will have 5 distinct roots. So the number of roots that you give me in the end is based on n. Let's see. So this right here, z sub k is new to this formula. That's how you can keep track of which roots you found. And down here at the bottom, it says for k, you're going to go 0, 1, 2, all the way to n minus 1. So think about it. If I said a cube root, that would be n equals 3. If I start at k equals 0, then I'm doing k equals 0, k equals 1, k equals 2. And I don't need to do k equals 3. I'll have my 3 distinct roots. If I do k equals 3, it will turn out to be the same thing as k equals 0. It's cyclical. Okay? And k equals 3 requires simplifying, k equals 0 doesn't, so we start at the least one. So then again, if we were doing like a fifth root, you would do 0, k equals 0, 1, 2, 3, 4. You always go up to one less. Okay? And that shows up in the formula, you do 2 pi k. Okay, speaking of 2 pi k, this formula assumes you are given an angle in what measurement? Radians. Okay, so if you work this formula out and your angles are not on the unit circle, which they won't always be in this particular problem, then you would have to change your calculator to radian mode. And we got to do that thing we did back in chapter 4 where we go in and out of radian mode. Or you could just amend this formula to be in degree mode. So what would you change about the formula? Add 360k. So I would write in my notes that an alternate version would be plus 360k, and this will be for degree mode, and hint, hint, wink, wink. If you use the formula in degrees, then you don't have to keep changing your calculator degree radians. So that might be helpful. Of course, that will change it down here. Instead of between 0 and 2 pi, you should then be between 0 and 360 again. Now, the version on the test will have the 2 pi k. So that would be on you to remember if you want to do the angle in degrees, that you change it to degrees plus 360k. Okay, let's do an example. We're going to find the cube roots for the complex number 8. This is basically KISS 2 pi over 3, right? Cosine 2 pi over 3 plus I times sine 2 pi over 3. What form of the complex number are you provided here? You are given trig form. So looking at your formula, all the things that you need to plug into the formula, this is great because we already know some things. What do we know? R is 8. We also know N. N is what value? 3, because we're doing a cube root. And we also know theta is 2 pi over 3. If you want to do it in radians, you can, or you can make the conversion here. 2 pi over 3 is what? 120 degrees. So I'm going to do it in degrees because I think it's a little bit easier. Okay. And the other thing that you have to plug into in that formula are your k's, right? Where do you always start k? 0, and then you go for as many roots as you should have, which will be 3, so I'm going 0, 1, 2 for k. It'll always be 1 less than your n value. Okay, so we're going to have to find 3 answers. I'm going to label them right away. Z sub 0, Z sub 1, Z sub 2. I've got 3 distinct roots. They're different answers for each one. And I'll just start plugging into my formula. What does your formula start with? A cube root of 8, an nth root of r. So we're going to do a cube root of 8. Okay, great. I know that's going to be 2. KISS. What do I do in the inside there? 120 theta plus, well, yeah, I mean, we're going to add a full revolution here, which will be 360, and then it's going to be multiplied by k, which is 0 for this one. So Pierce is doing that work in his head. That's going to be plus 0. And then divide by 3. Okay, n. So yeah, all of this stuff is just 120. What's 120 divided by 3? 40. So we got 2 KISS 40. there's one root. Now do another one. What's the only thing that's going to change on the z sub 1? K. The thing at the end. 360 times 0 is going to change to 360 times 1. But the r, the theta, the n, everything else is the same. So I just really have to copy this. Cube root of 8, KISS, 120 plus 360, change it to 1, divided by 3. I can do this without a calculator. Let's see, 120 plus 360, that's 480. Divided by 3 is 160. So I got KISS 160 degrees. That's a different one, different angle. So I got one more root to go. The only thing that's going to change for the last root, z sub 2, is k.
I figured out.
The k value at the end will now be 2. So everything else is the same. Cube root of 8, KISS, 120 plus 360 times 2, divided by 3.
I don't know if that'll work out.
Okay, that one's what? 120 plus 720, so 840. Divide by 3 should be 2, KISS,
280.
280.
Yeah, just
Tom, are you noticing a pattern?
Yeah, you just add theta every time. Like 120. Like you figure out the first one and then just add the angle every time.
I don't know that that will always be the case. But in this one, I am, like, what's the difference between 40 and 160 and 160 and 280? It is 120. But what are you actually, like, adding every time?
360.
The 360 divided by 3. So that's where your 120 is coming
yeah.
from, not the
Oh,
actual
so it's a
angle. Like, we could have a
coincidence.
different
It's just a
angle there.
coincidence.
Yeah. Okay, so it's the 360 divided by 3 is 120. So every time you increase k, it goes up by 120. So yeah, that's a great way to check your answers. Now, those 3 are my 3 distinct roots. If I did, think about this, if we use Tom's method and we add 120 to 280, what do we get? 400. And that's too big, right? So we would have to do coterminal angle. We'd subtract 360, which would get us to 40. And we would just repeat. So now we've got the 3 different roots. Okay, those are all in what form? Those are in trig form. Suppose I ask you for standard form. Don't worry, this one's going to be a little bit easier. If I ask you for standard form, notice these do not have angles from the unit circle. 40, 160, 280. So in order for you to get them in standard form, you're just basically going to do the components. 2 cosine 40. Make sure you're in degree mode. That's 1.53. And then I'm going to do 2 sine 40. That one has an I. So 2 sine 40 is 1.29i. Are you guys okay with where I got my numbers there? Okay. And then I would switch it up. I would do 2 cosine 160 and 2 sine 160. I'm going to cheat here. Negative 1.88 plus 0.68i. And then z sub 2 will be 0.35 minus 1.97i. So these will actually work really fast if you need to switch them into standard form because of directions. Now, on a quick side note, if I plot these standard forms, see 1.53, 1.29, negative 1.88, 0.68, and 0.35, negative 1.97. That's where my roots are. These roots actually sit on a circle with radius 2.
Oh,
You can't see it here. And then if you draw in their distances back to 0, it splits that circle into 3 equal pieces. So then it just goes cyclical. Like that's why it says distinct roots. We could keep going, but then they're just the same ones. Okay, do your homework and we will practice tomorrow.